Okay, so I want to talk a little about the two-body problem. This is just if you need some review for what we did in class, or if you're not in my class. This is just a little bit of sort of an analysis of the two-body problem for circular motion, so for circular orbits only. And so the classic two-body problem is where we have two bodies, unsurprisingly. So we'll call this, let's say this is, the one I used in class was the planet Pluto, so which has a mass of MP, and its moon Charon, which has a mass of MC. So, and they're separated by a distance r, and I'm going to make it a vector, so I'm going to call this like a, well, that's kind of an ugly vector. Let's see if I can do a little better here. That is slightly better. Okay, so this is our vector. You know, I like this one, it's thicker. Let me try just the thicker brush. So this is our vector r. Yeah, that's nicer. It's a little smoother looking. Okay, so this is the vector r going from Pluto to Charon, and we want to find, you know, how long it takes these two bodies, given that we know the distance between them, given that we know the mass of Pluto and the mass of Charon. So I'm going to underline all the knowns in this sort of light blue. We know all these. We want to find how long it takes this system to complete one cycle, and so the reason I'm not saying we want to find how long it takes for Charon to orbit Pluto is because in systems like this, it's not entirely correct to say that one body orbits the other. What happens is both bodies are moving a bit in relation to the center of mass of the system because they're attracted by each other. I mean, Pluto is exerting a gravitational force on Charon, right? So we can call that, F. But then Charon is also exerting the same force in the opposite direction on Pluto. And so because of that, Pluto is going to move. Pluto can't just be standing still, right? So what really happens is, think about the center of mass of the system, which we know is going to be somewhere, obviously it's going to be somewhere on a line between Pluto and Charon, right? The center of mass of the system. What happens, if these two bodies are just interacting with each other? If it's a closed system and Pluto and Charon aren't being significantly affected by outside gravitational forces, or maybe you could say, like, the sun is really far off and they're both orbiting the sun together, but they're both being pulled the same amount by the sun or the same acceleration from the sun's gravity, so you can sort of cancel all that out. But if we take a reference frame that's just fixed on the center of mass, then you recall our velocity of the center of mass is equal to the total momentum of the system divided by the total mass of the system. But if this is equal to 0, so if we're taking a reference frame that's fixed on the center of mass, and we're constantly moving with the center of mass, then the velocity of the center of mass in that reference frame is going to equal 0. And if the center of mass is not moving on our reference frame, that means the total momentum in that reference frame must be 0, right? So P total equals 0. And what that means is the mass of Pluto times Pluto's velocity plus the mass of Charon times Charon's velocity has to equal 0. And that means that if Charon is moving, then this velocity is not 0, which means this term is not 0. And that means this term can't be 0, which means Pluto must be moving. So what happens is they're both moving with respect to the center of mass. So there's some, Charon's got some velocity this way, and Pluto's got some velocity this way. So what's going to happen is they're both going to orbit the center of mass of the system. So for starters, let's figure out where this center of mass is, say just in this little snapshot. So to find the center of mass, what we do is we take, we find some reference point, and then we say the position of the center of mass relative to that reference point, which we're going to denote R, is equal to, and then you do this little product for each body in the system. You take its mass times its position with respect to that reference point. Okay, so that's once for Pluto, once for Charon. and then divide those by the total mass, or divide the sum of those by the total mass. And so you can see this is really, it's a lot like this, because total momentum would just be mass of Pluto times Pluto's velocity plus mass of Charon times Charon's velocity. This term, this equation here, or this expression, goes in up here. And so this is just the same thing. We just replace velocities with positions. So we want to find the position of the center of mass with respect to, and now we need to pick a reference point to use to denote a 0 for our vectors. So I'm going to pick my reference point here at the center of Pluto. So I'm going to say then that we're measuring everything from here. So what we're really searching for is, let me do this, I'll do this in like yellow, sort of. Yeah, it's not too visible. I'm going to try overdoing it with orange. Let's see. Orange is a little better. So what we're trying to find is RCM. This is in orange here. The position of the center of the mass, of the center of mass of the system with respect to Pluto. Okay, so we're taking everything here with respect to Pluto, everything in this equation, and so I'll do it in orange since this is what we're finding here. So the position of the center of mass with respect to Pluto is equal to, now this is the mass of Pluto times Pluto's position, but remember we're doing everything with respect to Pluto. What's Pluto's position with respect to Pluto? 0. It's in the same spot, so their position vector is 0. So this whole term becomes 0. And then the mass of Charon, what's Charon's position with respect to Pluto? This RC vector. Well, it's really just this big black R vector. Remember, it's kind of obscured now, but this R vector here is this vector that goes all the way from the center of Pluto to the center of Charon. So there you go. And then, of course, you just divide by MP plus MC. And so to sort of simplify this a bit, to simplify this a bit, what I'm going to do is I'm going to define capital M to be the total mass of the system, and that is just going to be Pluto's mass plus Charon's mass. And so what we get from that then is well, let's go back to orange, and what we get is position of the center of mass, position vector of the center of mass is MC over big M. So Charon's mass divided by the total system mass times this R vector. Now, if we want to find just, say the length here, we can take the magnitude of both sides of this equation, right? So we want to find the magnitude of R, because we know it's on this line, right? And we know it's going to be between Pluto and Charon. So, if we take the magnitude of this vector, then we don't have direction information in the vector anymore, but we know it's on this line. We know which direction the center of mass is going to be from Pluto. So let's just take a magnitude there, and we can say position of the center of mass, or the distance between Pluto and the system center of mass is this RCM thing here, and that's just MC over big M times the length of this big R vector, which is the distance between the centers of Pluto and Charon. That's simple enough. So that's our position of the center of mass. So I'm going to stop right there and then move on to the next video so I don't make these too long. So I'll continue with the problem in the next video.